Hello everyone. In the last video, we saw how the different on resistances of PMOS and NMOS created pulses which have got different rise and fall transition time, and due to that there was a pulse width. The pulse width check was failing because we expected a pulse width of 500 picoseconds, but we were getting a pulse width of roughly around 600 to 700 picoseconds. So this was the reason, the on resistance of the PMOS and NMOS being different, and basically the PMOS on resistance being more than the NMOS on resistance by typical 2.5 times. So that is the reason behind the unequal rise and fall transition time. In this video, let us try to find out a solution to this. So what can we do about this? So let's see what can we do. So what we'll do is, we'll take some analogy. We'll take an analogy of a box. So let's say the NMOS is represented by a yellow box. So the size of the box is this, what you see over here, and its resistance is R. Okay, and similarly, let us try to denote the PMOS as a green box whose resistance is 2.5 times of R. So basically, whatever resistance you see over here, this is just higher than that. It's like 2.5 times of R. So this is what the analogy we are taking. These are two boxes, and let's say the boxes are of equal size. So boxes are of equal size, but only the resistance of these boxes differs. Okay, or in other words, you can also consider this as a section of the pipeline, or section of a water pipeline, where this particular pipeline is completely open, and whereas this particular pipeline is a bit choked. And how much it is choked? It is 2.5 times choked. So that's why the water flow will be restricted in through this portion of the pipeline, and the water will freely flow because this complete thing is open for the water to flow. So let us take that kind of analogy. Okay, so we have an NMOS box with a resistance of R. We have a PMOS box with a resistance of 2.5 times of R. So now the size of the buffer size will be this much. So this will be your buffer size. So basically, the buffers that you see over here, that are of this particular area, so they occupy a very little area, or they occupy a very finite area, a very little finite area on the chip. So now what happens when we try to increase the reduce the resistance of the PMOS? So what can go wrong? So what can essentially go wrong? That is the second point. The first point is how to reduce the resistance of PMOS. So basically, the amount of choke that you try to reduce in this particular pipeline, the less will be the resistance. So what you can do is, either you can try to reduce the amount of choke, but that is not possible because that is the behavior characteristics of the PMOS transistors. Or you can do is, you can just increase the pipe size. You can just increase the pipe size so that the chokes, whatever present inside the pipe, will get a bit at the cider edges. So let's try to do that. If you try to increase the size of the PMOS, now the amount of choke that was available, that is still constant, but only you have got a more area for the water to flow. But there is a disadvantage to this, is the size of the buffer increases. So as we already said, that even a small area, even a small unit of area, square unit of area on a chip is expensive, is costly, because if you save a amount of area, you can add more and more applications to that chip. But in this case, this area size, or this increase in the size of the buffer is unavoidable, because we need, for high speed circuits, we need this kind of waveform. So this is unavoidable. So what are we doing is, we are increasing the size of the PMOS. We are increasing the area. We are increasing the area of the pipe for the water to flow, so that the choke, whatever is present, that is constant, but it gets moved. It gets slightly spreaded over here. So the choke, whatever is present, it gets slightly spreaded. So we are right now, still we are like 1.5 times of R. The resistance of the NMOS and PMOS are still not exactly equal. It is still 1.5 times of the resistance. It is still highly resistive, and it is possible, if we use this kind of buffer, it is possible that this particular waveform might be a bit better it might come somewhere over here, but no, it won't be as good as the one which we have sent at the input. So what we'll do is we'll try to increase the size of the buffer even more. So let's try to do that. So now the buffer size increases because the PMOS size increases, and but the resistance decreases. That's a good news for us. As the resistance decreases, it's not yet completely equal to R, but it's 0.5 times of R. So it's not completely reduced, but the resistance has reduced to a significant amount. And what we can see is, by using this particular buffer also, you might get very close to this one, but it's always better to maintain a good equality of resistance between the NMOS and the PMOS, to avoid scenarios something like this, which can appear at any corner of the chip. So we want to try to avoid that particular thing. But again, as you have seen over here, when you increase the size of the PMOS, your buffer size increases. Again, there is a penalty on the area, and this is a huge penalty compared to the initial one, which was like only this much. This was the initial area. Now we are like 2.5 1.5 times, or twice more than that particular, or even more than twice. You can actually place 3 regular buffers over here, so it's 3 times more than the initial buffer size. But there is no option to this. We have to do this to in case of high speed circuits, and in case of performance we need to do this. So what we'll do is we'll try to increase the size of the PMOS even more, and now the resistance of the PMOS exactly matches with the resistance of NMOS. So in this case, we are very sure that the waveform that you sent at the input and the waveform that you get at the output, both will have the same rise and fall transition at the output. That is the thing that we can assure with this kind of buffer. Basically, the PMOS size has increased, and you have you have a very least resistance that the PMOS is now offering, and basically the resistance is very similar to the one which NMOS is offering, but the penalty is that the buffer size has increased. Imagine this amount of buffer size being placed at every intervals, at every area. So imagine the increase in the buffer size that you are obtaining on the chip. So that is a problem. That is a penalty that we have to pay. So there are optimization techniques which we will be talking in the further slides. There are techniques to optimize this particular thing, but for now, if you implement if you replace all these buffers with this kind of buffers, there is a penalty in area, but there is also a gain in the performance. So it's okay. For now, it's okay to have a small area penalty with a gain in the performance. That is, right now we are fine with that. So what we'll do is, now we will again do the same experiment where we had tried to send the input waveforms and tried to collect the output waveforms. Let us try to do that again. So let's say now this is the input waveform, basically the from 0 to 1 rising edge that we are sending over here, and at the output of the inverter we expect a rise to fall kind of waveform, which is like this. And this was already good because the NMOS is still the same, so the discharging is is similar to that we had at the input side. So the discharging was never a problem for us. So you see a transition. Basically the input rise to fall, fall to rise, and output rise to fall transition are more or less the same. Basically what matters for us is the output transition time, rise to fall transition time, and the fall to rise transition time should be equal. So in this case, let us try to calculate that particular value first. So the high to low transition time is, let's say, T1, and the delay is, let's say, D1. Delay is from this endpoint to this point, and let's call the delay as D1. Next we will be sending the fall to the rise to fall transition time, the high to low pulse at the input of the inverter, and at the output that you get is you get a sharp waveform which is very close to the input one, or which is very close to the one that we saw in the previous case. So the fall to rise transition time is now exactly equal to the rise to fall transition time, and the reason for this is now the charging current will flow through the PMOS, but the PMOS is bigger in size. Bigger in size, which means it has got a low resistance. It has low resistance, which means the resistance is very similar to the one which we had for the NMOS. So in this case, the transition time, the rise time will be faster, the capacitor will, or the output will get charged faster, and you see this kind of transition time, basically fall to rise transition time. Now if you calculate the delay, it's exactly it's exactly the same. It's again D1. We have got rid of the delta factor over here, and also we have achieved that we have come to a point, we have come to a very healthy conclusion where we say that the rise to fall, fall to rise transition time is now very equal to the rise to fall transition time. Basically we have brought a solution into the picture which says the transition time, the rise transition time and the fall transition time are equal. We have almost found out some solution to that. We will again look into some optimization techniques, but till now we are happy about that we have a solution. We had a problem and we had a solution to that. So let's see what we'll do is, since now I'm running out of time, we'll take this particular solution in this particular chip and do the quality check analysis again, because we are again modifying the clock tree. So as and when we modify the clock tree, we need to do the complete we need to fill the complete checklist again. So what we'll do, we'll try to look all this in the next video. Thank you.